So I've been, you'll see a little bit my CV, but I am at the University of Edinburgh. I'll also tell you a bit about the University of Edinburgh, so if you're not aware of it. I have a very strange position. So I am at the university full time, but my salary is paid by a company. So I work also for Canon Medical. It's one of the big providers of scanning equipment for if you take a scan, if you go to the hospital. And I also have a fellow. So a fellow means you're affiliated with other institutions of the Turing Institute, which is the equivalent of Archimedes in the UK, in London. And I'm also an Ellis fellow. Ellis is the European Laboratory for Intelligent Systems. It's a pan-Europe organization about AI. Our website is Bios, means life in Greek, okay? And then you can also email me if you have any questions, or you can find me on Twitter. All right, why don't we start it? So we're talking about safety, right? And my way of lecturing or teaching or talking is very Socratic. So I will ask you questions and you expect answers. And I will not continue until I get answers, okay? Yes, right? So that's why I only have 10 slides. No, I'm not joking. Anyway, so why don't we go? All right, so how many of you have an Amazon Echo or a thing? So it says here, no, Alexa, I said order lunch, and then the rocket goes up, right? So now it's just a way to think about safety of something that you think so benign, like a smart speaker, and how easy it is to confuse input, okay? And particularly if you're Greek, have learned to speak English from watching TV, and then your wife is Italian, and you've lived also in Italy, so my accent is a mess. So my devices never understand anything. They understand my daughters though, which is funny. Anyway, so that's about safety. So before we get to that, I want to tell you a little about the University of Edinburgh. How many of you have ever been in Edinburgh? That's good. For the fringe, for the festival. You live there, sorry. The hearing is not the greatest after all this cutting of the grass outside. So anyway, Edinburgh is up here in the north of the UK. I've been there about 8 years now. It's the 6th oldest university in the English-speaking world. I don't know what that means. And we're a pretty big university, and we are the oldest AI university. It's been founded, the AI department was founded 60 years ago, okay? And I have here some famous, this is the old college, where the university was initially based. Now there's campuses all over the city. And I just have some pictures of famous people and see if you can recognize them. See, first question, first test. Can you recognize them? Huh? Watson? No. He won the Nobel Prize on particle physics. Higgs. Now, what about this old dude? Huh? He's very famous for a theorem in statistics, in probability, how to turn a conditional probability to a joint Bayes. This guy, very famous for appending the world in terms of evolution, Darwin. And this guy? I was expecting that you all know this. Hinton. So Hinton is considered the father of modern AI. He used to be a professor at the University of Edinburgh. And when AI died in the late 80s, it was one of the big winters, he had to leave and he went to Toronto and he established a new group there. And things were laid dormant for 20 years, and then now we have what we have now. Okay. So anyway, so quiz number 1 passed. Okay. Now let's go next. Just so you can understand the accent, I'm from Thessaloniki. Okay. Then I lived for 10 years in Chicago. Then I lived for 4 years in Italy, and for the last 8, I'm in Edinburgh. highly recommend you go to all places. This is called the Bean. It's a statue, is a sculpture in the middle of Chicago. This is the Amphitheater. Is one of the oldest and unique oval piazzas in the world. So it's not round, it's not circle, it's oval. It's very nice. Lucca in Tuscany. I don't know why I left. Um, but yeah, it's a very beautiful place. Very nice for the Tuscan tour. All right, so I lead a group in Edinburgh where we do what we call interdisciplinary AI. So we tackle problems where we think AI can help. The problems actually inspire the AI solution, right? So it's not truly theoretical, it's not truly applied, it's somebody in between. And we do things with people all over the world. We collaborate extensively, and we are always open to people coming for a visit, coming for a month, a couple of months. If you want to experience a bit of different groups, how they work, if you're interested in research or anything, you're more than welcome to come. So, I'll tell you a bit more about things that the problems that motivate us, and then we'll get started about safety. So, have you ever heard of the H pyramid? Yes, it doesn't look like a pyramid anymore, right? It looks terrible. We're definitely getting older as a Earth, and at the same time, there's a lot of diseases that we still have to fight for. We have to still fight, particularly if we want to make, let's say, the same quality of life for everybody around the world. And I'm a true believer that AI will help, okay? I truly believe that. Otherwise, I don't think I will be able to wake up in the morning. I truly believe that, but we are still a very long way to go. So how many of you have gone without 24 hours of hearing on the news that AI will take our job? Everybody heard it, right? How many of you have heard like AI did something bad in the last 24 hours? Everybody hears. Even my mom asked me yesterday. I went to visit them over the weekend, and she said, "Can you give me an account for ChatGPT?" And I said, "What would you do with ChatGPT?" "I need to know." Exactly. So mom is always right, and you always have to make accounts for your mom. All right. So now, very briefly, I'll tell you a bit the focus areas of our research. So we work on what we call data representations. So to computers, an image is numbers. To a computer, let's say this is an EKG. It's like as a time series, numbers. Text, numbers. They cannot understand them. Somehow they need to be able to extract information from them as a way to do AI or as a way to do statistics on them. So that's one focal part. The other focal part is how we create a lot of synthetic data from simulations, and how can we create or learn AI without having to collect data, right? Very recently, we have a large program of work on causality. And I know Evie mentioned before causal fairness and causal counterfactuals for fairness. And we talk a lot about, and we work a lot on the value of data, privacy, and so on. And this is what I will focus mostly today, okay? Now, before Evie asked you about how many of you come from health, so I wanted to give you a bit. Imagine that you wake up one day and you say, I'm going to work on these problems, and I want to, develop a solution that's going to end up in the hospital, okay? And I have the privilege of being able to do that, and I see how painful it is. So I want to tell you a bit about the painful process, okay? So most people think, okay, I'll pick a problem. Let's say I'm going to work on cardiovascular disease. I will find some data. I will collaborate with hospitals and collect some data. Then I will have to find clinicians to label the data, give me some good ground truth. Then I'm going to develop the AI. Then I'm going to evaluate the AI. Is it going to work very well? Is it safe? Is it robust? Then I'm going to get it certified. And then I will deploy it. And here I use the venerable National Health Service in the UK because it's a good example of what it means to deploy solutions at large scale, okay? Now, where do you think is the hardest problem in all of this? Not easy. No, easy. No, easy. Certification. Mm. No, deploy. You don't know how long it takes to procure and do a competition to deploy the solution in the NHS. If you have a team, I'll tell you a little bit about the budget that goes around here. Where do you think 5% of our budget goes? Huh? Develop the AI is 5% of the budget. About 30% goes here, okay? 30% goes here, and all the rest goes here. Okay? So a lot of people think completely, because we are always in the research domain, and you think, this is a problem, and we can all of this, and it's very frequent where we have the engineers and the scientists say we can improve the AI, and you always have the people that go and hunt for data, okay, and they go look for new relationships and build more data, and sometimes they find data quicker than the AI gets developed. So at the end, some of the simplest solutions actually tend to work. So you'll be surprised that the solutions that are actually deployed now in the NHS are actually very, very simple in terms of novelty or in terms of AI-ness. Okay. So all the examples will be cats and dogs. Okay. So I guess yesterday you learned about what is deep learning, right? So that's good. And you also learned about the idea of classification, but not with cats and dogs. Huh? You did machine learning, but you didn't talk about neural networks. A little bit, that's enough. A neural network, a deep network is basically a very, very deep neural network, so it doesn't make a difference. But what is fundamentally important to realize is that you start from photos of the objects. Here is a classification of cat versus dog. And as you go down, information gets thrown away. And the only relevant information retained is the one to make the decision. Okay? And this is very important for you to realize. Now, what do you think is useless information to throw away here in order to make decision of cat versus dog? The background, yes, somebody else? The color of, but sometimes, everybody, all the cats are pardales now, so you can imagine the color may be confusing. But does it matter whether the cat looks straight on the camera or to the left to decide whether it's a cat or a dog? No. So in fact, the pose of the cat's face, it's irrelevant, right? So we call this invariance. So we want to throw away information that makes the decision irrelevant, right? It's not relevant for the decision, so we throw away this information. Now, here is the funny part. The things that, a lot of the things that Evie told you about comes from this fact that this thing has to throw away irrelevant information and retains what it thinks is relevant. So if suddenly identifies a statistical bias towards something, it will retain that statistical bias because it's easier to make the decision. This is known as shortcut learning, and we will talk about it later. Now, here, I start with the question, are AI models safe? And I think, okay, I live in the UK, so I'm biased. But the UK is pretty advanced in terms of, also with Europe, it's pretty advanced about what do we think about safety. They produce a lot of this, what we call policy documents. And I can send you a couple of links, but are very easy to find in general. And they contain a lot of information about particularly if you come from law or ethics, about how different countries perceive these things. Now, for myself as a scientist, as an AI scientist, sometimes I find all the ethical aspects of a slowdown, because sometimes before we act, we overthink, and we work in a very competitive field. There is 1,200 papers being submitted every day in AI. So we are always in a global competition, right? So we always want to do ethical research and ethical work, but at the same time, things can get too slow. Because somebody asked a question before, and I thought that was relevant to mention that. So, are AI models safe? What does it mean safe? What do you think? What would you consider safe?
Depends on who is affected by the safety. I can say this way. What do you say safe for the society, for the person, for
You, okay, fine. Think of it as a clinical problem of a device that's going to be used in a clinical setting. So safety, yes, go.
Something that
You can trust. So it doesn't cause harm. Somebody else? You wanna?
when it comes to clinical, then we also have definition of health as body, mental, and societal
Okay.
well-being. So if the insurance
Is your phone safe? Is your mobile phone safe? Probably not, right? But we still use it. Do you go in the car? Do you smoke? A lot of people still smoke. It's not safe, but we still smoke. But think from the point of view of safety. So I put this picture here because I went and looked at this document on how they define safety for what an AI should be, right? And they have these words here. First word that came is generalizable. Have you heard of the word generalizable? We will define all of these things as we go along, right? So AI can generalize outside the training set. The second thing that came out as safety is robust. An AI should be make consistent decisions. Okay. Third, fair, which is what Evie told you before the previous hour, makes decisions independent of protected characteristics or protected attributes. Okay. It's my definition, but it's a kind of like shortened version. And explainable. AI can explain the decision. Okay? So, more or less, this is how the majority of these policy documents consider what safety means. Okay? In which of these have you believed that we have made the most progress? The robustness? Somebody else? In which one do you think we have made the majority? Yes.
I think XAI, explainable AI, is.
We have made the most progress. Okay. You have something to say? Huh? All right. So generalizability is what's considered a holy grail in AI, right? This is a problem they've been working from the last 60 years. Okay. And it's very tied to robustness, and it has to do with invariance, and I'll show you this example. Fairness, now there's been a lot of progress. Explainable, now it doesn't work very well. Because the way it tries to do it, there is a lot of things about explainability, and there is explainability in a different context. So if you want to create, if somebody gives you like some variables like the gender, the age, your weight, whether you're like, your ancestry, et cetera, it's very easy to build a model that can predict, let's say, your cardiovascular risk. Is that model explainable? Yes, because if the model is linear, it will tell you, I believe you're very risky because 30% I give as a weight to your age, 20% to your gender, etc., etc. So that automatically is explainable. And a model becomes non-explainable, the more complicated it becomes. Okay? Right? There's a very beautiful word in AI, it's called parsimony. Okay? Have you heard of it, parsimony? It means basically simplicity. And our brains tend to think about in a very simplistic fashion. Have you heard of the Daniel Kahneman's thinking fast, thinking slow? He won the Nobel Prize, I think, 20 years ago. Can somebody buy him coffee? Can buy the guy a coffee? Anyway, so and it turns out that our brain has what we call system 1 and system 2. And system 1 is something that is ready to make impulsive and easy decisions, right? And that's simplistic thinking. And we like this simplistic thinking. And you know why our brain likes simplistic thinking? Think of biology, huh? Think as a biology, huh? It's energy efficient, it consumes less calories. Making hard decisions, like think about trying to study for an exam, right? You have to take, After a while, you're tired, you want some chocolate, you want a coffee, because it consumes energy versus, simple, easy decisions and instinctive decisions. You can make them like that. So, the final one is trust. And trust is a very overloaded word, I think. As we said before, fairness is an overloaded word. I think trust is an even more overloaded word. And anyway, so let's talk about generalizability. So we will have here this is a space where the data lie, okay? Don't worry about what it is. So there's gonna be some data here that represent the dog, and there's gonna be some data here that represent the cat, and we will learn a classifier that separates the two, okay? So generalizable means that if I have another cat picture here, I expect to behave very well. But sometimes, maybe I've never had in the training set cats dress as sharks. So you can see here that I will still like, even though that the training set may not contain dressed animals, right? You will still be able to recognize that this is a cat, okay? So that's what generalizability is very, very important. Now, generalizable, that didn't help. So generalizable is a holy grail problem in AI, and the number one solution is what we call regularization. So, and the only thing we can do in some sense is control how that line will be drawn, given the few data that we have. Fundamentally speaking, this is the only solution that works. Robust. Robust is something simpler in concept. So let's say here I have a picture of a cat, and here I have this picture of the same cat but flipped around the y-axis. Okay, so you can see the paws now are to the left versus here they're to the right. So I wanted to make the same decision independent of the fact of how I took the picture. Okay, that's robustness. So tiny changes do not affect the decision. Okay, that's the definition of robustness in an AI sense. Explainability, very, very hard. So now here, if you notice here, I drew names on the axis. I said here, flappy ears. I came up with it, okay? And here I said less vertical pupils. So very vertical pupils here, less vertical pupils here, okay? It's just a contrived example. It doesn't make sense at all. So the idea is that the dogs have like ears that flap around, and they're more likely to be a dog if you have floppy ears. Cats, have these eyes that look like slits, right? Particularly when they're happy and not annoyed. It's more likely to be a cat. So that's the idea. So if you now suddenly throw a picture, you would expect the AI to tell you that this is a cat because it has pointy ears, it has vertical pupils, it has a gray pattern, it doesn't smile. Apparently dogs smile. They have facial features because they have muscles here that control their faces versus cats don't. Wants to attack the owner at any time. You will hope it will tell you that something about the cats, right? Now, we don't have this. We don't have systems that can take a picture and explain why a decision has been made. We don't have that. Okay? We really don't. We have some hacks, but they don't work. Okay? We don't have what we call human explainable, a readable explanation of why we make decisions. Of course.
What if you ask another AI system to explain the results?
Yeah. So what do you mean by another AI system?
For example, ChatGPT.
Okay.
If you feed it with this information,
You feed it the picture, or you feed this? The picture. ChatGPT, the current version still doesn't take pictures. The next one will. Yeah, the next one will. Yes, so that is what's called image to text, okay? So it will basically try to describe the picture. Now, internally, you can imagine that it's having lots of different classification tasks internally. And that's how it builds the final text, okay? So there are people there are groups that do try to combine these ways of explaining an image in text and also using that as a way to justify the decision. There are definitely efforts on that. It's easy to think about in a contrived example of cats and dogs, but once you talk about like healthcare applications, it's it's hard to develop data sets where you can have somebody explain and write the AI. Do you know? So I don't know about ChatGPT, but there is another company called Stability AI, right? Stable Diffusion. Do you know how many image pairs of image and text they used to train that machine? 1.5 billion. So some poor person distributed across the world talking about equity, about how we build AI actually by leverage cheap labor elsewhere. One point, somebody wrote down for every picture an explanation, like a small 50-word caption for 1.5 billion pairs. Okay, so that's how it was trained. We cannot do this in other data, and I'm sure we should be doing it, to be honest. Now, talking about generalization, I wanted to offer you a bit of an explanation of how we useless scientists sometimes think of data, okay? And particularly when I talk to my students, I use this example and I ask them, how does a tomato look like? How do you think a tomato should look like? And they all think like this. Nice, plum, red. You know, you don't have to touch it, don't squish it ever. You know, they don't let you, but it should look like this. But in reality, tomatoes are beautiful. They're full of diversity. There are different varieties, different sizes, different colors. So if you build an AI to recognize tomatoes that looks like this, then of course it's not going to work when it's going to face with all the different diversity that exists. Now, some of these tomatoes are going to be very, very, very rare, right? We don't eat them, they don't taste very well, but they exist. Now, how we will go about creating an AI that is going to work very well, even for things that we rarely see. So one of the biggest problems of AI today is extrapolating to the unknown. It's not extrapolating towards a tomato that's going to be a little bit greener, or it's going to be a little bit dirty, or it's going to be a bit like squished. Oh, that's a good idea.
Yeah, because I think it's a bit
Yeah.
too hot.
Yeah. So, and the biggest problem is that how do we identify AI that can work with rare data? And if you're working health, everything in health is about rare data. Do you ever go to the hospital if you're feeling fine? No. Do you ever go to the doctor if everything is I just want to see you? No. You don't go get tests done unless something is wrong, right? So nobody's really, everything is about rarity and everything is about very complex. Now, training data, because I think a lot of these things gonna relate about what we discuss about how do we train models. In healthcare, there are two different types of models, two different types of training data. One, we call it consented data, where users agree to share the data and all related but anonymized personal but protected information, okay? This is consented data. I specialize in this category. Sorry, I'm going to that. And some of the examples, so there's the UK Biobank, where the government is basically collecting the data, volunteers, they go take scans, they take blood tests and so on, and they collect them, almost 1.5 million now people They're collecting the data. There are other ones that come, for example, for dementia from the US. And this one is very interesting. This is actually every individual can go and upload their medical records online on a website for helping research, okay? So you can see these are examples of consented data, but I specialized in unconsented data. So how do we create AI sitting behind a hospital, right? So, and we create what we call safe havens, where you can imagine these computers are not connected to the internet. They are what we call air-gapped. They get information from the databases of the hospital. There is a checklist here happening where we make sure as much as possible to clean up and anonymize information. Then there's a data scientist here and a researcher using the data to develop an AI solution in this air-gapped computer. And then there is an output here, and this output here happens in a very strictly controlled manner that no information not allowed exits. So you cannot export data, you cannot export individual information about patients and so on. So everything happens within the safe haven, okay? So that's what my specialty is. So some of our projects happening, for example, across all the Scottish population, 1.7 million patients. So we have access to all the imaging brain scans of all patients in Scotland and so on. There are a lot of interesting questions though. What happens if this process here is not perfect? And nothing is perfect, right? Nothing. Well, babies are perfect, but okay. But the second thing is that what happens if the process here that controls what's coming out is also not perfect and some information leaks? So how do we check and make solutions to these problems? So for the next 5 minutes, I'll give you an example of what happens if something escapes here and whether the AI can use that bias as a way to make decision, okay? So, and to motivate this a little bit, I want to show you an example from COVID-19. Now, that's not our work, but it's a very famous example. So you have, this is an image of a chest x-ray, okay? And it's the very first test that they will do if you go with lots of cough and fever at the hospital, because they want to look at, is the lung here, this is the lung here, this is where the heart is. Are they looking whether the image is clean or kind of like messed up? Because it means there's fluid or some other stuff. I'm not a doctor, so don't quote me. Now, they created this AI and they found out that sometimes the AI will make decisions not by looking at the lung, right? But by looking at particular things that happen outside the image. So this is what it says is supposed to be an L here. Is the classical thing that the doctors will put when they take, well, the radiographer will put when they take an image to know is this the left shoulder or the right shoulder, okay? And you can see one here, L, and you can see here an R. It's that they actually put like a sticker there, and it's made out of lead, so you cannot, the rays do not penetrate, so you can only see the R, okay? The other thing that you can tell is that this AI will look at the gaps here and try to see these gaps and try to tell whether this picture and read these gaps as a way to identify actually the size of the patient. So he used, Evie told you before about this proxy. Do you remember the proxies? The zip codes, the postcodes is a proxy for gender. These gaps here are a proxy for weight. Okay? So rather than creating an AI that was able to detect whether a patient has COVID or not, the AI found what we call shortcuts and read, this L there, this means it's coming from that hospital. That hospital is on the front line of COVID. It has high likelihood of having disease, COVID. It's all COVID. So it will learn this information here, as a way to make the decision and not look at the lungs. Okay? So this type of shortcut learning is the biggest risk that we have today with these deep learning models. Okay? And I'll show you here some work that we've done just to tell you a little bit more about shortcuts. And to get you to start there, we will have to come up with a little bit of definitions. So we will have, let's say, an input X and the output Y. And we would like to think about these types of what we call spurious correlations, right? Spurious means that they're not real. They are just related, but they're not real, okay? They can either be related to the label, or they can either be related to the input X. And I'll give you now some examples, okay? I'll try to go, hopefully you can see them. So sometimes these correlations, the spurious correlations can be related to the label, right? They happen in a very rare fashion. So here is, for example, sometimes the process, some of the machines will imprint on the top of the image the name of the patient. So you need to have a sanitization process that will read if there is a name and cut the picture. But sometimes that fails. Maybe it fails 1 in a million, 1 in 1,000. But if you're working with, let's say, 2 million patient records, even 2 is enough, right? Or this is one of my favorite ones. This little kid went for an X-ray of the wrist, and the mom is holding, well, the mom or the dad is holding the hands of the baby, but there is also a pig here, because the baby or the toddler wanted also the favorite toy. So there is a Peppa Pig now in the data set. Sometimes they can happen very frequently, right? So you can see this type of markers that I showed you before. These exist. Or sometimes you have artifacts that come from the type of scanners used. All of these things happen in real data. So if you want to make an AI that is robust, right? The solution, people think, well, I'm going to clean the data up. I'm going to clean off all of these things that are happening. That's not the solution. That's not the solution. You cannot clean up things that sometimes you cannot even see. So I'll show you here examples of things that you cannot even see. So one type of thing that happens is ghosting. This ghosting happens in the background, and it's invisible to the human eye. You have to do specific pre-processing to see it. Sometimes it happens just because there is a rare anatomy. So here is a patient that had a prosthetic eye, and it looks completely different, the prosthetic eye, from the real eye in the picture. All of these things create complications for when you're devising and building algorithms. This is what real data, remember the picture of the tomatoes before, right? That's the full picture of the tomatoes. Not clean looking tomatoes like in the supermarket, but all type of tomatoes. So I'll show you here an example of a very interesting experiment that we ran. So we wanted to simulate what will happen if, let's say, we have an image of an X-ray and somehow the name is written on top, right? And we made it to the extreme. We said, what if we have a data set and there is only one image in the data set that will have a name, and this letter A here is the equivalent of a name. Okay. The question is, can we check whether an algorithm trained on this data set, rather than looking at the rest of the picture, will look at the letter A to make decisions? Because if you can prove and you can show that an algorithm, even with one image in the whole thing, having this problem, right, having this leakage, what we call here, that this sanitization process failure, it's still likely to be detected. This means that it's going to get worse if you have more, right? So it's basically what we call a sanity check. So, and we wanted to ask another question, make it even more difficult, to say, can we do it in a black box setting? And I'll explain to you what I mean by black box. Black box setting is, a lot of the times, you are, as a researcher, you want to test the performance of an algorithm, but you don't have access to the innards of the algorithm. You only have access, the ability to give it inputs and read its outputs. Okay, this is called a black box setting. You cannot see in the box, right? You don't see the weights, you don't see the design. So this is the most, I would say, heavy way, the most scrutinous way of judging whether AI is fair, biased, and everything. Okay. So, and we did something very, very simple here. So we found data sets from other types of images, not related to what we knew is our input. And we created here, we have a clean image, an image with a letter A, and another image of something that looks like a letter but is not a letter. And we inputted all of these results into the model, and measured the outputs. And we then did a statistical test that compares these outputs. If the model is biased by the letter A, this output should be completely different compared to this one, right? And it should be completely different also between these two, okay? So effectively, if the confidence of the model changes when it sees the letter A here, an image with the letter A, this means that it has a bias towards this, right? And it sounds very simplistic, but the outputs are very depressing. And it's so depressing that it's basically things of what's called memorization. So it doesn't memorize the image, it memorizes the letter. And memorization is a very big problem in AI today. Because if something can be memorized, guess what? If an AI model can get memorized, guess what it can do? Yes. Not be changed. Yes, but what else? Imagine that I sold you a phone and it has an AI model inside that has also been memorized. And somehow you got the phone. There is a particular risk with memorization of data. Can you think of that?
It's not safe.
It's not safe, but what does it mean safe? For whom?
It does not protect the data.
If the data have been if the model has memorized data, you can always define a function, a process, to regurgitate the data, to extract them. So can you imagine the risk of AI models being able to, what we do, invert and regurgitate the data back? That's a huge risk. So, and on top of that, we found that this risk is completely random. This is different models trained. Sometimes it happens, sometimes it doesn't. If we don't know, this is the worst thing that you can do when you train models or in science, in engineering. When things are random, we hate randomness. Because if it's random, guess what? We cannot control it. Okay? And then we also tried different standard tricks in AI, and none of them work. So you have an effect that is completely random, and you cannot fix. Out of a simple experiment that showed that even just one single image with just one failure of a previous process of cleanup allowed us to show that we can create an AI that memorizes, it's biased to that letter A. If that letter A is maybe something related to gender, it can be also unfair, anything you can imagine, just out of this idea of what we call shortcuts. And for that AI, it was easier to read the letter A and make a decision rather than learn the content of that image. Now, imagine I showed you here the examples of that letter A on this data set that is very simple. But imagine the risk from a decision standpoint, right? So imagine if I go back to that image here. And here it says Jane Doe. And let's say for Jane Doe, this Jane Doe has emphysema. So the AI has learned a shortcut between the name imprinted here, Jane Doe, and emphysema, right? What will happen in another image? Suddenly the name Jane Doe appears. You will think it's emphysema. Now you see the clinical risks of something that might be happening. So shortcuts are a huge danger today in AI. And this type of memorization, it actually has even more risks. And if you're interested in all of these things about this type of what we call privacy attacks on data, we have a long survey if you're interested. And it's actually 2023, not 2213. I'm not an alien traveling back in time. If you're interested, it talks about all these different types of attacks and what happens to the models. Now, the second part, I guess, how long do we still have? 5 minutes? Yeah? Yeah. Huh? So let me show you examples of, Olga, what did you say? 5? Okay. So I'll show you one example of memorization in another context, and then we'll stop there. So, so I showed you before that these AI models memorize, right? It's not my day today. So this is a very interesting experiment that was done a few years ago on large language models, right? The ChatGPTs, the BARDs, and everything. And it's very interesting. They found that if they send this as an input to the large language model and they ask it to fill in the gaps and I didn't do that. I didn't move. It found. I am an alien. I'm a legal alien. I'm an Englishman in New York. So you can find this pretext, and somehow, just by giving this information, he was able to completely regurgitate a whole sentence from the data verbatim. So large language models memorize like hell. They're full of memorization. Okay? Large language models, what they do is what they call compositional. They do a compositional learning. So they learn a little bit from there, a little bit from there, a little bit from the different texts, and they try to synthesize them. But once in a while, you can find the right prompt to directly extract information from the model, verbatim. Okay? Now, and these things tend to become even more problems when you start using the data supposedly from the internet, and somehow you are revealing the data that you were trained with, and then somehow you took a very relaxed interpretation of what's free in the internet and doesn't have copyright. And I think this is going to be one of the biggest things that might change what will happen in AI over the next 2 years. If these lawsuits, there are 4 lawsuits now happening simultaneously in the US. If any of those win, all of these things about generative AI will completely slow down because they have all been trained with what we call dirty data. Okay, and I'll stop here.